Hello and welcome to another video on another math question. This one was question 5 from the 2012 math paper. Now, yeah, I think this one's a tough question. I really do, particularly at the end. It starts off really nice, starts off really easy. I think that the first 4 parts are really straightforward. But then you look at the mark scheme and realize the first 4 parts are worth 6 marks. The last 2 parts are worth 9 marks. Obviously, they don't tell you that, and that's a little bit of, always kind of I don't know why in both the step and the mat they don't tell you how many marks each question's worth. I don't see what's the big deal is. Why not tell everybody? But there we go, they don't. And yeah, that came as a surprise to me because I was thinking, oh, I've probably got quite a few marks here, more than half. Yeah, I think I did get more than half, but it was part 6 where I really broke down and found it very tough. 5 as well. It's easy to go wrong on 5, but we'll have a look at that in a second. Okay, so let's start this. We've got a little robot in a program. Do have a go at this first so you know what I'm talking about. He can only go forwards 1 unit or turn left a quarter turn right a quarter turn. And we've got a program which is a sequence of these commands. Now it starts off, P0 is just move forward 1. The next program though is the last program, then turn left, same as the last program, then turn right. So this is going to be a recursively building program. So if we try and write down P2, and they've written down P1 for you because it's going to be F, then left turn, then forward 1, then right turn. If we write down P2, well, we need the previous program, which is forward, left, forward, right. But then we need to turn left, and then we're going to do again forward, left, forward, right, and then we're going to turn right. Yeah, so it's important to recognize how this is building up in complexity. Now, okay, how far does a robot travel during the programming PN? In other words, how many F commands does it perform? Because traveling is when you're moving forwards, not turning. Turning is not we're not traveling when we're turning, we're just turning on the spot. So, okay, well, we can see straight away P0 has got 1 F in it. P1 has got 2 Fs in there, yeah? And that's because you're repeating the last program twice, but then you're turning. And so it's just, when you go from P0 to P1, you're just going to double the number, double the distance basically. And when you go from P1 to P2, you're going to double the distance. And that's because now we're going, however far we traveled last time, which is 2 Fs, and then we're turning, and then we're going to travel the same distance. Well, that's why we're doubling it, because P appears twice here, and then we're going to turn right. So yeah, this is 4. It's pretty obvious that P3 is going to be 8, I hope, because we're just going to do this, then turn left, then we're going to do this again, and then turn right, and so there's going to be 8 Fs in there. So this one's pretty easy to do. It's simply 2 to the power of n, because look at that, 2 cubed is 8, 2 squared is 4, 2 to the power of 1 is 2, 2 to the power of 0 is 1. So it's just 2 to the n is distance. And I don't think they want you to prove it here, but if I did want to justify that, I'd just literally write a sentence or two, and I probably would. In fact, I have on my own solutions I've written down, it's pretty clear that Pn travels the distance 2 to the n because each time we repeat the previous steps twice, so we're doubling distance each time. Yeah, moving from moving from Pn to Pn plus 1 requires going twice the distance. So it's like an inductive argument. Distance in PM. Yeah, so there we go. I've written a little sentence to justify it. I suppose just be on the cautious side, just to make sure we definitely get the marks. Okay, so let's keep going. Part 3. Let Lm be the total number of commands formed in Pn. So for example, L0 equals 1, L1 equals 4. Yeah, write down an equation relating ln plus 1 to ln, and hence write down a formula for ln in terms of n. No proof is required. That's nice. So they don't even want the proof. Okay, well, looking at this, yeah, L0 is 1, L1 is 4. We can work out L2 as well because we've got P2 written down, and we can see that's a string length 10. And L3, well, how do we get from P2 to P3? We do this, that's 10 moves. Then we turn left, that's 11. Then we do this again, that's another 10, we're up to 21. And then we turn right, 22, yeah? And hopefully you can see here, each time, going from ln to ln plus 1, you need to double the number of commands you did in ln, and then add on 2 which represents this L and this R. Yeah, so we're doubling it because we've got two PNs there, and then we're adding on the two extra commands which are in this sentence, so we get 2ln plus 2. So that's not too bad either. That's part 3. We have got a little bit more on part 3 though, because it says hence write down a formula for ln in terms of n. Yeah. Oh, sorry, ln. Yeah, I've got that ln. That's cool. Sorry about my L's. It almost looks like lun there. That's why I was getting a little bit confused. But okay, right. So it asks us specific to look at ln plus 2. So I will do as I'm told. Now that's a plus 2, a big plus 2. If you think about the sequence, actually, I'm not going to write down what it equals. I'm just going to think about the sequence. Yeah. So if we look at L0 and add 2 to that, we get 3. If we look at L1 and add 2 to that, we get 6. If we look at L2 and add 2 to that, we get 12. When we look at L3 and add 2 to that, we get 24. Now, I hope you can see straight away that is a lovely geometric sequence. And so, what can we say? Well, this geometric sequence will have term 3 times 2, a times r. Now, normally it'd be n minus 1, but we're starting at 0 here. And so it's going to actually be 3 times 2 to the n, because that way we get 3 times 2 to the 0, which is 3 for L0. 3 times 2 to the power of 1, that's 6 for L1. And so what I can say is ln add 2 equals 3 times 2 to the n. And therefore ln, I've got the formula now, 3 times 2 to the n minus 2. So that's why they got you to look at ln add 2. It's easier to recognise that it's clearly a geometric series. Okay, so far so good. Not too bad, fairly typical as well. They love putting in geometric series in these kinds of questions. Okay, the robot starts at the origin, facing the x-axis. What direction is the robot facing after performing the program Pn? Good question. Okay, well, if you look, and if you really think, let's have a look at P0. It's facing the x-axis. P1 turns left once, turns right once. Must be still facing the x-axis, because if you turn left and you turn right, it's like you haven't turned at all. P2, turn left, then right, then left, then left, then right, then right. Well, the order doesn't matter. As long as there's as many L's as R's, you're going to be facing the same way. And there will always be as many L's as R's, because the definition, the inductive step, has one L and one R in it. And you start off, if you like, with just one L and one R in on P1 anyway. On P0, you've got 0 L's and 0 R's. So you start off with an equal amount of L's and R's. And so after performing this program, there's going to be the same number of left turns as right turns. Hence, it must be still facing the origin, no matter how many times, sorry, not facing the origin, facing the x-axis, looking to the right, no matter how many times you do it, because for every left turn you do, later on you do a right turn, which cancels it out. And so, yeah, all I need to put here is we will always be facing the x-axis. As for every left turn, as there are an equal number of left turns and right turns. Of L's and R's. So hopefully that's nice and clear for them. Now this is where it gets difficult from part 5. They want us to draw P4. So this is what we've got. Yeah, I like to build this up actually. I'd like to point out, okay, they drew P1 here, but actually P0 is here because P0 represents F. Do you remember that? And it's interesting seeing how we move from P0 to P1 because P1 becomes FL, FR, yeah, and that's because the rule is Pn plus 1 is Pn L, Pn R, yeah. Well, what is this really doing? It means that we can see that when we move from P0 to P1, we're basically thinking, I've got to do P0 again, yeah, and I know this is, I almost wish that I hadn't, can I just, I'm just going to move the screen over, yeah. If you're thinking, how do I get from P0 to P1? All you've got to do is think, well, all I've got to do is do P0, then turn left and do P0 again, whatever P0 was, forwards. And I get to that, yeah? And then turn right. But remember, I already know at the end of any command, I'm always facing in that direction, yeah? Now I'm going to use exactly the same principle to try and work out how to get from P1 to P2. Because this formula still holds. It's always the same thing. You basically repeat the command you did before, turn left, and then do the same command again. So if you still know that P1 is like this. Yeah, you're at P1 when you get here. Well, you know you're looking in that direction. And so the first thing you're going to do is turn left and do this shape, but like rotated 90 degrees because you've turned left. So it's going to be like that shape on the end of it. And so that's like where you are after P1, and this is where you are after P2. And you can check that that works. But essentially, that's what this formula is describing. It's saying take the last pattern, apply it again once, then turn left and put the same pattern on the end. Yeah, that's what we're actually doing here. To get from P0 to P1, we did that. To get from P1 to P2, we're going to do that. And this is super important, this recognition, because it really helps us in the last bit of the question. So how do we get from P2 to P3? Well, let's get rid of this P1. We know where we are now at P2, and we know we've got to do P2. Now remember, you're always facing this way at the end. We're then going to turn left, and we're going to do P2 again. In other words, we're going to draw this shape again, but we're facing this way now. And so it's going to look like that. So you're at that point at P2, and you're at this point at P3. You see what I mean? So each time I'm just taking the pattern before, turning left on the end of the pattern and placing the pattern down from there again. Yeah, and that's how we're working it, because that's what this inductive definition is describing. It's saying do your last pattern, but then turn left and do the same pattern on the end of it. So to go from P3 to P4, I realise I'm here at P3, and I'll tell you what, I'll do this in a different colour. And now I've got to remember, I'm still facing left at the end of this. Sorry, I keep saying left when I'm looking right. You're facing right, yeah? You're turning 90 degrees, and then you're going to repeat this pattern again. So I've got this pattern. Yeah, that's the pattern I'm looking at. But I want to like rotate the whole pattern 90 degrees. And so that's going to take me, I'm going to go over that line, go like that, and then I'm going to come back out and come back in and do that. And that takes me from P3 to P4. Hopefully you get what I'm saying there. Basically, it's the same pattern. Then turn left when you're at the end of it, because remember, you're always facing to the right. You turn a quarter turn, anti-clockwise if you like, and then you just place the pattern down again. And that's how you get from one pattern to the next. That's super important, because that's going to help us with the last part. Now, that was worth 3 marks, and I think basically the last part is worth 6 marks. So that's big marks in this, and this was definitely, for me anyway, one of the toughest questions on this paper. Okay, let xm, ym be the position of the robot after performing the program Pn. So x0, y0 is that, x1, y1 is that. Give an equation relating xm plus 1, y plus 1, ym plus 1 to xm, ym. Well, this is exactly what we were just talking about. We were saying basically, if you want to go from Pn plus 1, if you want to go from Pn to Pn plus 1, you have to repeat this twice. Well, let's put it like this. Do once, turn left, do again. So do once, turn left, do again. Don't worry about the right on the end, because we already have established that you're always facing to the right at the end after doing these, and we can use that as our principle. So what we need to do, we need to think, well, how do you rotate something 90 degrees? Well, lots of ways of doing this in maths, actually. Firstly, I'd say from what you know with matrices, you can easily work out the matrix rotation, which takes you your points from there around to there, because it's quite clearly 0, 1 minus 1, 0. Yeah, if you know about matrices, I would personally just take xn, yn, and I'd multiply it by this matrix to work out what what the rotated coordinates will be, and it's going to be that times that, that times that plus. Let's do it properly. Yeah. Okay. It's a way I've written it down. Let me just budge it over. I've written it down backwards, haven't I? I was wondering why it wasn't working. Anybody who was screaming at the screen there, good for you. 0, 1, minus 1, 0 times xm, yn. Now the matrices are indeed conformable. Okay, right, now we can do it. When we multiply out this matrix by this coordinate, we get that times that plus that times that minus ym. That times that plus that times that is going to be xm. Yeah? So what am I saying here? I'm saying if you go, say, and I can do it on my screen because I've got squares. See that vector which goes 2 across and 3 up? I don't know if you can see the squares on my board. Well, if you did instead, so that's vector 2, 3, The right angle vector to that, the one which is rotated, and you can hopefully see it once again on my screen because it's working, would be -3, 2. Yeah, that's how you rotate a vector by 90 degrees anti-clockwise. The other way of doing it, of course, if you're in the complex plane, for all those complex numbers enthusiasts, just times by I. If you times by I, you rotate a complex number 90 degrees. And so if you consider this xy, if you like, x plus yi, if we just times that where xy is your initial coordinate, treat it as xm, ym, if you times that by I, you get xi minus y, because I squared is -1. In other words, you get minus y plus xi. In other words, in your coordinate, you get minus y for your x coordinate and x for your y coordinate. See what I mean? You can just times by I to rotate 90 degrees clockwise. But anyway, so there's a couple of ideas for how you find the rotation. But you can almost just work it out in your head. But this is not an easy part of the question. That's why I'm taking a while explaining it. So anyway, what does all this mean? Let's put it all together. I now, I think, can work out what xn and yn is in terms, sorry, what xn plus 1 and yn plus 1 is in terms of xn and yn. Because to get to the next point, I need to take where I was after applying Pn once, and then I need to turn left and do the whole thing again. Well, turning left and doing the whole thing again would be the same as adding on this position vector here onto that. It's probably best seen with numbers here. Can I show you it with patterns? We were doing P3 and P4, yeah? Clearly, P3 has coordinates -2, 2, yeah? What I'm saying is to get to P4, what I need to do is travel -2, 2. But then because, and if I can do these with vector notation, that's essentially your vector, which takes you from the start to P3, -2, 2. And then I need to add on to that the effect of turning this one 90 degrees. And like I say, I've already worked out how to do that. I just add on. Do you remember I wrote down, let me write down the formula so you can see it. Xn plus 1, yn plus 1 is xn yn plus minus yn xn. And so what we're going to have here is the negative of this one, -2, and then the positive of this one, which is also -2. And when you add them together, lo and behold, you get -4, 0, which is exactly where we are here. Do you see what I mean? It works, and it works because we've basically said, okay, we'll represent that first move as a vector, then we'll represent this next move as a vector, and we get to P4. It's clever, it really is. I actually noticed this when I did this question. I didn't notice the formula. I'll be perfectly honest with you. This bit got to me, it really did. I worked out the formula. I did work out the formula, but I tell you what, I didn't work it out in a traditional way, not like this anyway, not with vectors. I worked it out because I just wrote down the first 4 coordinates, and I noticed that it was xm minus yn and xm plus yn. So you might do it like that. Now, using this, you can easily work out x8, y8 because you already have x4, y4. Yeah, x4, y4 is, of course, this -4, 0. It's P4, -4, 0. So we've got -4, 0 is x4, y4. I'm writing mine down as vectors. They wrote theirs down as coordinates. It doesn't really make any sense, a difference. But I just wanted to show you what we're really doing here is moving around the page with vectors. So I could easily work out x5, y5 now, and I could just do this a slow way. And this is the slow way. There's a quicker way, which I'll show you in a second because we need it for the second part. But I could now just do, so take them away. You're going to get -4. Add them together. You're going to get -4. So that's x5, y5. x6, y6, take them away, you're going to get 0. Add them together, you're going to get -8. x7, y7, apologies for my handwriting, it's getting worse. Take them away on the top, you're going to get 8. Add them together on the bottom, you're going to get -8. And then finally, x8, y8, we've basically done it now. Take them away, you're going to get 16. Add them together, you're going to get 0. So that's x8, y8. Yeah, and this is tough, this bit, no doubt about it. But like I say, you could have worked that out because you can actually get this formula just from looking at the coordinates and noticing. It's not easy, but The key thing is when they got you to draw out P4, I think, to recognize, oh, it's just the previous pattern, turn left, put the next pattern on again, and that helps. Okay, what about the very last part of this question? X8K, Y8K. Well, this is tough. What you have to do, once again, I didn't notice this myself. I just, when I gave up and looked at the mark scheme, I'm like, oh, I get it. Yeah, okay, I see what they're doing. But I don't think I would have got this in exam conditions. Right, we'll write it as coordinates. Okay, xn plus 2, yn plus 2, I can work out in terms of m, because I can say, well, this is xn plus 1 y minus yn plus 1, because you always just take away for the x coordinate and add them together for the y coordinate. But I really want this in terms of n's. But I can do that because I already know that xn plus 1 is just xn minus ym. And yn plus 1 is just xn plus ym. And it's the same over here. I can do exactly the same thing, xn minus yn plus xn plus ym. And I can simplify that. And what do I have? Well, I have x minus x. I'm going to have 2yn here. And I'm going to have here 2xm, positive 2xm. What are we saying here? We're saying if you want to go 2 moves ahead, what you need to do is you need to, your new y coordinate is going to be your yn coordinate swapped with your xn, basically swapped into the x position and multiplied by minus 2. And your old x coordinate, double it, that becomes your new y coordinate. So that corresponds to that one, if you like. And this one corresponds to this one. So to find your new x coordinate, 2 steps ahead in the program, take your old y coordinate and times it by minus 2. That's your new x coordinate. And take your old x coordinate, times it by 2, and that becomes your new y coordinate. Okay, so I hope that helps. Now, why does that help? It's because we can now work out xm plus 4 ym plus 4 using the same sort of step twice, yeah? Because I now know how to go 2 ahead. That jumps me 2 ahead. So I'm going to go back to m plus 2. So this is minus 2ym plus 2, because this is just saying I need to reduce 2 from my old y coordinate. So I've reduced 2 from the y coordinate and times it by minus 2. Same here, 2xm plus 2. But then I can just kind of recursively use this idea, because how is ym plus 2 related to yn and xn? Well, ym plus 2 becomes 2 times xn, so that's minus 4xn, and likewise this is going to become minus 4yn. Cool. So we know that xm plus 4, ym plus 4, if you want to go 4 steps ahead, that's what you need to do. Okay, the last one, because then we've got xm plus 8, yn plus 8, and therefore, remember as well, if you know how to go 8 steps ahead, this is basically saying what is the general position every 8th application of the program. Every time you've applied the program 8 times, or any multiple of 8 times, what's the general coordinate? So let's just do this once more to find out xm plus 8, ym plus 8. Now, what we need to do, this is how to go 4 steps forward, so we need to apply it again. Basically, if you want to get 4 steps forward, you need to take your x coordinate from 4 ago and times it by 4. Take your y coordinate from 4 ago and times it by 4. And we can relate this back to xn and yn, which is what I'm really trying to do, because xn plus 4, I already know this is minus 4xn, so I get minus 4 times minus 4xn, and here I get minus 4 times minus 4yn. And so I'm going to get 16xn, 16yn. Yeah, so this is a way we can relate 8 steps forward in the program. Now this could have given us immediately, without the way I did it, without this recursive way, this could give me x8, y8. Let me quickly show you. We already know p0, or x0, y0 if you prefer, is 1, 0. Right, now I can just apply this method to find p8, because they are 8 ahead. You just need to do 16 times the old x coordinate and 16 times the old y coordinate, 16, 0. Exactly the same answer as what we did doing it the long way round. What about if we're doing 8k? Well, can you see that P16 here is going to be exactly the same move? We're going to have to times it by 16 again, both coordinates. And so this is going to be 16 times 16, 256, and 16 times 0, 0. P24 is going to be x24, y24. Guess what? We're timesing it by 16 again. And so what is 16 times 256? That's like 2 to the power of 8, I think. Multiplied by 2 to the power of 4, 2 to the power of 12, 4,096, I think. Yeah. But who cares? Because what we really need is x to the 8k, y to the 8k, y subscript 8k, I should be saying. Well, can you see this is clearly going to be 16 to the power of k, 0. Wow, that one's a hard question. Hardest one I've seen on that paper, I think. It's not an easy question. Apologies for my handwriting here as well. Hope you enjoyed the video. Keep up the good work. Bye-bye.